So what I want to discuss in this video is the second derivative test. Okay, so we just finished a little video on concavity, and when we discussed concavity, we talked about the fact that the second derivative was less than zero, or the second derivative was greater than zero, and we went in x less than zero. This is concave down. Okay. We went in and did a problem where we talked about setting the second derivative equal to zero, finding out those points of inflection, right? So anytime we have the second derivative equal to zero, this is a possible point of inflection. And if there is a change in concavity, then we can identify that point as being a point of inflection. So if the concavity changes from positive, or the concavity changes from concave up to concave down, then we have a point of inflection. Or if we have a situation where our second derivative was positive and now our second derivative is negative, again, that x value right there is going to be a point of inflection. So in this video, we're talking about the second derivative test. And the second derivative test does not determine, it doesn't tell us anything about the concavity. You'll notice the second derivative test helps us find out where the local extrema are. Okay, so it says it right here. The first derivative test provides an analytical tool for finding local extrema, but the second derivative can also be used to do this. Okay, so let's take a look at a couple here. There is a little bit of reading you can do, but what I wanted to do was just go right to this picture. Okay. So in this picture, we have this point A. And at point A, you'll notice that the first derivative is equal to zero. I know that's the case because the tangent line is horizontal. Okay? But really what we need to focus on is what's happening with these tangent line slopes. Here we have a very positive tangent line. And on the other side, we have a very negative tangent line. And what that tells us is as we move from left to right, those tangent lines are decreasing. In other words, f prime is decreasing. To say f prime is decreasing is to say that f double prime is negative, right? And you can see that played out right here. Likewise, down here at the bottom, we have a minimum. And what we want to note at the bottom there is that f double prime is greater than zero. Okay, so to say that f double prime is positive, right? That's really what that means. F double prime is positive implies that f prime is increasing. Okay, so we can see our tangent line is very negative, and as we go from left to right, that it becomes very positive. So that's a signal that our first derivative is increasing and our second derivative is positive. So the consequence of all this is that if f double prime of C is greater than zero, we have a minimum. This is the opposite of what you might think. If f double prime of C is less than zero, we have a maximum. And then if the second derivative at C is zero, then we have an inconclusive test. Now what we want to point out to you though is C. C is that critical number, okay? And we get a critical number by our critical point. We get a critical point by setting the derivative equal to zero. So let's take a look at an example and kind of break down how we're going to do this. I'm going to come over here to my blank screen. I think it's a lot easier for you to see how all this is played out when it's just worked out on a clean sheet of paper. So our function is f of x equal negative 3x to the fourth plus 4x to the third, okay? And what we want to do is find all local extrema. So we said that the first derivative is a great way to do that. The first derivative test is a good way to do this, but the second derivative test will also work. So let's go through this. In order to find the local extrema, you need to remember that local extrema occur at critical points. Okay, so again, a critical point is where the first derivative is equal to 0. So we have negative 12x to the third plus 12x to the second. We're going to go ahead and I'm going to find the second derivative right here, just because we're going to need it. Negative 36x squared plus 24x, okay? But what I have to do is I've got to set this derivative equal to 0. Now, you notice that we have 12s right here. I'm going to divide everything by 12. And then I'm going to factor out a negative x. And that leaves me with a negative x squared. That leaves me with x plus 1. Or x minus 1. And if I set each of those equal to 0, I see that I have 0 values or I have critical values or critical points at 0 and 1. Okay? So if we're breaking this down and looking at, all right, what was step 1, what was step 2? Step 1 is finding that derivative. I went ahead and found the second derivative in step 2. Step 3 is where I go and find those critical points, right? Because again, that's where local extrema are going to occur. So I'm going to find those critical points. And then step 4, we're just going to plug those critical points into the first derivative, okay? So negative 12 times something to the third plus 12 times something squared. And the values that I'm plugging in are in right here. Sorry, I lost my pen. The values that I'm plugging in are going to be 0 and 1. So I'm going to come down here and do this twice. And the reason that I'm doing this twice again is because I have 2 critical values. I think I put a 1 right there and I should have put a 0. Sometimes my pen doesn't write what my head is saying. So we have 1 here, 1, and 1. Okay, so I've plugged in 0 and I've plugged in 1. Okay, so 0 to the third is 0, right? 0 to the second is 0. So if we combine all this, f prime of 0 equals 0. So here the second derivative test is inconclusive. Same thing down here, negative 12 plus 12, we get 0. So we see that our second derivative test is inconclusive. So we can see let's see. Yeah, their derivative right here had an issue. So the PowerPoint's a little bit wrong on this one. There were 2 critical values at 0 and 1. So you might want to go by what I have here. This will be one of those PowerPoints that I need to go back in and adjust. These are from the publisher again, so I apologize for any mistakes. However, I think if you'll follow along here, you'll see exactly how to do that. All right, so in both cases, this test is inconclusive. Let's try another one of these and see if we can go through our steps again, just to make sure you're on the right page. When that test is inconclusive, remember, you can always go do the first derivative test, okay? So let's work one out right here. X to the third minus 3/2 x squared. Of x equals x to the third minus 3/2 x squared minus 36x. And again, what we're doing is we're going to use the second derivative test to locate all extrema. For which values does f of x have a local minimum? Okay, we're looking for, in particular, a local minimum. So because we're going to use the second derivative test, we do need to find that second derivative. But before I can do that, I've got to go find those critical values. Okay. Well, before I can do the second derivative test, excuse me. So I'm going to go ahead, remember in that last video, I went ahead and found the second derivative. We're going to come over here and set this first derivative equal to 0. Again, the reason we're doing this is to find those critical points. So I'm going to have, I'm going to go ahead and divide everything by 3, and I end up with x squared minus x minus 36, minus 12. X squared minus x minus 12. So 0 is going to equal x minus 4 and x plus 3. Those are 2 numbers where I'm getting the derivative equal to 0. So I'm going to go plug these values. Again, I'm plugging them into the first derivative. So f prime of 4 is going to equal 3 times 4 squared minus 3 times 4 minus 36. So let's see, this is 3 times 16. We know that's 48 minus 12 minus 36. Again, we're going to get 0 here. We don't always get 0. These just happen to be two of the problems where we do. F prime of negative 3 is going to be 3 times 9 minus 3 times negative 3 minus 36. Okay. So we're going to have 27 plus 9 minus 36. And again, we get 0 there. So taking a look at these, right? Let's see. Did I miss something here or did the textbook? Let's see. To determine.